Hello and welcome to follow this presentation of our work, Refined Core Relaxation for Core-Guided MaxSAT Solving. I'm Ihalainen and we did this work together with Jeremias, Berg and Matti Järvisalo. So our work is about improving algorithm for maximum satisfiability problem, MaxSAT. And MaxSAT is an optimization version of the well-known Boolean satisfiability problem. In MaxSAT, we've got a set of hard clauses that must all be satisfied and a set of soft clauses with different weights. And our task is to find assignment to the variables that satisfy all hard clauses and minimize the weight of the unsatisfied soft clauses. There are many different proposed approaches for solving MaxSAT, and we are improving core-guided approach. So on core-guided approach, a SAT solver is used and the algorithm does multiple different calls on SAT solver. And between the calls, the formula on SAT solver gets transformed into a new version. So this is core relaxation step. And in this paper, we concentrate on the question about how to improve this core relaxation step. So how to make these transformations of the formula on SAT solver in such a way that it would all the time be as easy for the SAT solver to solve the formula as possible. So our contribution is that we propose an improved, a new way of encoding kernel constraints in the context of weighted MaxSAT. And we call it structure sharing technique. Our technique decreases the size of the encoding and improves the propagation properties of the encoding. Then we show that the proposed technique is effective in practice as well as in theory. We improve two different core-guided algorithms with it, and another of them is a state-of-art MaxSAT solver. And then in our paper, there is some new insights about the weight-aware core extraction technique. Weight-aware core extraction technique is a technique for core-guided MaxSAT algorithms in which the core relaxation step is delayed as much as possible. And our work depends on building cardinality constraints for a set of cores at a time. And to enable this, we use weight-aware core extraction in our work. So here's the outline of this presentation. First, preliminaries, then overview of Ovl Algorithm, which is a state-of-art core-guided algorithm for MaxSAT. Then we introduce our new proposed techniques. Then follows empirical results of our techniques, and finally, we overview related work. So weighted MaxSAT is a set of hard clauses that must all be satisfied and a set of soft clauses that have each cost for not satisfying it. And from now on, we assume that each soft clause is a unary clause of a negation of some blocking variable. And this type of transformation is well known, and it can be done on any weighted MaxSAT easily. So from now on, we may talk about weights of blocking variables instead of weights of soft clauses. And core-guided algorithms depend on SAT solver having an assumption interface. So basically, SAT solver checks the satisfiability of its formula when we set some values to some of the variables in that formula. And in our context, we basically add hard clauses to the SAT solver and then handle soft clauses via assumptions. And since soft clauses correspond to blocking variables and also assumptions correspond to soft clauses, these three are all a bit interchangeable in this work. Then the concept of unsatisfiable core. So a subset of soft clauses that cannot be satisfied together with the hard clause is said to be unsatisfiable core. And in the context of SAT solver, a core is a subset of assumptions that cannot be satisfied together with the formula SAT solver has. So now to the Ovl algorithm, and we begin by general overview of core-guided algorithm. So on core-guided algorithms, we init SAT solver with hard clauses and set soft clauses as assumptions. And then we check on SAT solver whether we can satisfy all our assumptions together with the hard clauses. And if we cannot, we get an unsatisfiable core from the SAT solver, so we get a subset of our assumptions that cannot be satisfied together with the hard clauses. And we relax that core, and we iterate this until we can satisfy all our assumptions together with the hard clauses. And the idea of relaxation step is that we allow one blocking variable in the core to be true. So we allow not satisfying one of the soft clauses in that core. And how to implement this relax? Different core-guided algorithms do it differently, but here is what Ovl does. So to allow one blocking variable in the core to be true, we basically allow blocking variables in the core to be true, and then we limit the number of true blocking variables to 1. And allowing blocking variables in the core to be true is done by removing them from assumptions. But because we are dealing with weighted MaxSAT, here we also handle the different weights of the blocking variables in the core. So actually the algorithm decreases the weight of each blocking variable in that core by the minimum of all weights of the blocking variables in that core. And this is also known as close cloning technique. And then a blocking variable is removed from assumptions if its weight is 0. And limiting the number of true blocking variables to 1 is done by adding new blocking variables to the instance. And each of the new blocking variables is said to be equal to some cardinality constraint over the blocking variables in that core. And we set these new blocking variables equivalent to cardinality constraint by adding CNF encoding of this equivalence to the SAT solver. So this is the step we are improving, how to add these cardinality constraint encodings to the SAT solver. And to get an idea of that, we first try to get a general idea how this encoding can be done. So how to encode cardinality constraints in CNF form. A common way is to use totalizers. So totalizers is basically a rooted binary tree, and in our context, we set the variables in the core as leaves, and the new blocking variables will be in the root. And in this structure, each node has a number of variables that will have values that are basically the values in the leaves of that subtree, but in sorted order. So the figure on the right gives an idea of how this works. And this effectively encodes the cardinality constraints over the variables in the leaves. So what can we improve in this? First, we observe that on weighted MaxSAT, the different cores may share a number of common variables. And this actually made it redundancy in the totalizer encodings. So here's an example of what could happen. Two different cores which both have variables B3 and B4 in them. And both have a subtree where B3 and B4 are as leaves. And now, both these totalizers, when they have this type of subtree, actually the whole subtree is equivalent in these two totalizers. So instead of building 2 times a this type of subtree for these two variables, we could build this subtree once and link it to both totalizers. And this is the structure sharing, basically. And in this way, we need less variables and less clauses to encode these two cardinality constraints. But doing it in the context of core-guided MaxSAT isn't so easy, because normally how the core-guided MaxSAT algorithm works is that once core is fine, we build a totalizer for it, and its structure is fixed then. And not all possible totalizers enable same amount of structure sharing. So we need to have common variables in the totalizers, but also a structure where the common variables are in same subtrees. And this isn't obviously always the case, as can be seen here in the figure. So to be able to share structures in the context of core-guided MaxSAT solving, we would like to build totalizers knowing which variables we should set to same subtrees. So we would like to have knowledge of different cores when we build totalizer for a core. And this is enabled by weight-aware core extraction. So to get an idea about weight-aware core extraction, what is the idea behind it? Here's an example of MaxSAT instance. And it has three blocking variables, B1, B2, and B3, with weights 2 and 1 and 1. And the instance has two cores that concern us here, B1 and B2, and B1 and B3. So assume we first find a core B1, B2. And normally what Ovl does, we reduce the weights of the variables, and weight of B2 is then 0 and it is removed from assumptions. Then we build totalizer for B1, B2 and add new blocking variables to the instance and then continue finding new cores. But now, weight-aware core extraction is based on the observation that we don't have to build totalizers and do any changes to the instance after we have reduced the weights and removed B2 from the assumptions. But we could continue extracting more cores, and we can actually, in this case, find core B1, B3 without making any more changes to the instance. And for what is important in this, from the perspective of our work here, is that we end up in a situation where we are building totalizers for a set of cores rather than for a single core. So our structure sharing algorithm uses weight-aware core extraction to get a set of cores and then builds totalizers for that set. And when we build totalizers for a set of cores, we can maximize the amount of the number of shared subtrees in that totalizer structures. So next, the other question. So how does structure sharing improve propagation properties of the totalizers? So we defined new blocking variables of Ovl being equivalent to Kernel the constraint over the blocking variables in the core. But it is well known that the implication is actually enough for the correctness of the algorithm. And many implementations only add implications, because if we add only implication, we need less clauses to encode the constraint. And it is also known that equivalences lead to more propagation in the structure. And this is especially the case when totalizers share subtrees. So this is new result in our work. So when we share subtrees and add equivalences, it can lead to some interesting non-trivial propagation in this structure. And let's see an example of it. So we set three values on this totalizer structure. Let's see first what happens if implication clauses are only added. So two values propagate with implications. And next, if equivalence clauses are also added, we propagate four more values. But the interesting thing here is that when we look which values caused which propagations, we notice that the values on the left-hand side totalizer are actually causing propagation to the right-hand side totalizer. And this wouldn't actually happen without structure sharing. And we conclude that structure sharing, when equivalence clauses are added, can help SAT solver to find some interesting relationships between the variables of different cardinality constraints encodings. So different, yes. So what we actually did in practice, since adding all equivalence clauses is expensive, we decided to use heuristics to select when to add equivalence clauses and when to not add them. And we ended up adding equivalence clauses in only some parts of the total structures. And we try to maximize the situations where the equivalence clause could actually propagate something interesting. And at the same time, we don't want to add too many equivalence clauses, since they may also slow down the algorithm. So to the empirical results. First, here we show that the structure sharing successfully decreases the sizes of totalizer encodings in the context of MaxSAT. So we run a number of MaxSAT instances on two versions. Another version used structure sharing and another didn't. And structure sharing version successfully decreased the size of totalizer encoding, sometimes even dramatically. And more importantly, we improved the overall performance of the MaxSAT algorithm. So on the top figure, we integrated structure sharing as part of RC2, which is a state-of-art MaxSAT solver and implementation of OLL. And we see that with structure sharing, we are able to solve more MaxSAT instances and we improve the running times. And below it, we integrated structure sharing also as part of another different core-guided MaxSAT algorithm than OLL. So we used PMRES algorithm. And also here we see that structure sharing significantly improves the running times and number of solved instances. Then we also did some tests about equivalence constraints. And here on the top is the same figure as in the previous slide. And below it, we have a figure where the different RC2 versions are using equivalence constraints also when building totalizers. And the version where we use heuristics is the fastest one in here also. So some overview about related work. There's been an idea about extending a single totalizer with more inputs. And our work is about multiple different totalizers sharing some of their inputs. Then WPM3 core-guided MaxSAT algorithm. They've got some interesting insight about the question what to do when outputs of previous cores occur in new cores. And finally, structure sharing in a different context. So actually, they've got very similar idea of sharing structures between totalizers, but they do it in the context of ANSYS programming. And we do it in the context of improving core-guided algorithms for MaxSAT. So conclusions. What we do in our paper. We introduce structure sharing technique to improve totalizer encodings. And we decrease the size of encoding kernel constraints and improve the propagation properties. We show that the technique we propose is effective in practice. And finally, we provide some new theoretical insights of WCE. And all our implementations are available online. Thank you.